Okay, so this lesson's going to be on to sample, z-test for the difference of proportions. So the first part of 10.1 was finding a confidence interval for proportions. So now we're going to talk about how to do a test for to sample, and we're just talking about proportions. So everything's in terms of z's, okay? So for your test, your null is going to be that the difference is 0. So you can either write that like that or like that. Either one is perfectly fine. I've never heard anything about the graders preferring one method over the other. So now look at your alternates. You could have the difference between the two is greater than 0. Okay, but now look to the right. That would mean that p sub 1 is bigger than p sub 2, because when you subtract them, you're getting a positive difference. Or p sub 1 minus p sub 2 is less than 0. That means the difference is negative. Well, if that's the case, then p sub 1 needs to be smaller than p sub 2. Okay, so you can write that either way. And then you can just write that the difference is not 0, aka p sub 1 does not equal p sub 2. Your conditions, random, is the same. Independent, 10% condition for both sample sizes. Watch your sub 1, sub 2, or if you do sub M for men and sub W for women. For your LCC, and these have hats on it, these should not have hats because you are going to know what P is. Okay, tell you what, let's just say we're not sure if they're going to have hats or not, okay? And let's read the information and make that decision instead of trying to memorize when they have hats and when they don't, okay, for the LCC. And for your standard deviation, for your test statistic, let's stop trying to memorize it and let's let the problem tell us what are we given, because you know that you always want to use P instead of P hat if you can. Now your null and your alternate will always be in terms of the parameter, so no hats, okay? Your test statistic is exactly the same, but here's what's going to go in it. So your statistic is P hat sub 1 minus P hat sub 2. So it's the difference, and you have to write that out. And then minus your parameter are the two population proportions subtracted, which will always be 0. Then you have your standard deviation of the statistic. And so you've got P, so you've got P1 Q1 over N1 and P2 Q2 over N2, and we'll figure out if we need hats or not based on the problem. So we'll figure that out in a second. Okay. Now, let's talk about, because we're going to adjust our Z, okay? If P sub 1 equals P sub 2, which remember is your null hypothesis, okay? Then we're saying that the true proportions are the same. If they are the same, we're going to call their common value P sub C as the pooled or combined sample proportion. Okay, so we're going to replace the P sub 1 and Q sub 1 and the P sub 2 and the Q sub 2 with P sub C and Q sub C for both of them. So guys, these numbers right here are going to be the same, and these Q's are going to be the same. Now, your N1 and your N2 will not be the same. Two different, well, unless you have the same sample sizes, but two different samples, so probably two different sample sizes. Now, to figure out what your P hat sub C is, your pooled proportion, you're going to take the total number of successes from both proportions, add it together, and then you're going to take the total number of trials from both proportions, add it together. And that fraction, that ratio, which you're welcome to turn into a decimal, is going to be your P sub C, or your P hat sub C. Now, please make sure that you understand that doing this is not the same as doing that. So you cannot just, like, let's say this one's 25 out of 30 and this one's 26 out of 30. You cannot find P sub C by doing 25 out of 30 plus 26 out of 30. The algebra does not work like that. What you have to do is your P hat sub C, and it's going to have a hat on it because this is sample data, is going to be 25 plus 26 over 30 plus 30. So 51 over 60 is your P hat sub C. Okay, so this is the sentence you're going to hear me say a lot to help you remember when to pool your proportions. It's only on a 2-sample test. It's not on an interval. It's only on a test. And so my mind has to come up with some stupid way to help me remember. And so here's how I remember it. So, okay, way back in the day when I was in high school, I used to be a lifeguard. And we used to always have to test the chemicals in the pool. You see where I'm going with this? Pool, test. Not on an interval. You only pool your proportions on a test. So where you have a null and an alternate, because you have to test the water in the pool. You do not interval the water in the pool. You test the water in the pool. So that's how I remember it. You only pool on a 2-sample test. And obviously it's only for proportions. It's P sub C. So you're not going to have this for means. Okay, so this next problem should be completely written out in your notes. Like you have all the work, everything. So we are just going to talk through it. So I'm just going to kind of highlight, because guys, you've done tests. You've done a whole bunch of tests. Okay, so this should be very similar structure. Okay, first thing, we are 2-sample z-test for difference of proportions. You absolutely have to define both your variables. It's not like a matched pairs where you can just do like mu sub d. So this one I have to have a P sub 1 and a P sub 2. And notice those do not have hats on it because we are defining our parameter. And that is the population information, which is P, not P hat. Okay, let's read the question first. Here we go. Researchers designed a study to compare the proportion of children who come to school without eating breakfast in 2 low-income elementary schools. A simple random sample of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, a simple random sample of 150 students included 26 who had not had breakfast. More than 1,500 students attend each school. Does this data give convincing evidence? That's how I know it's a test. At the 5% level of significance of a difference in the population proportion. It's not asking which one's bigger than the other. It just wants to know, is there a difference? Okay. And I hope you guys can see that you have 2 completely separate samples here. So it does not make sense for this to be a 1-sample matched pair. It's not 1 sample, both going through 2 different treatments. This is 2 separate sample sizes. So P sub 1 is the true proportion of all students at School 1 who did not eat breakfast. Do not get lazy on me here at the end on defining your parameter, okay? P sub 2, true proportion of all students at School 2 who did not eat breakfast. My null and my alternate, well, the null is always The first one minus the second one equals 0. And for this one, it wants to know, is there a difference? So my alternate is that it doesn't equal 0. And then there's my level of significance. All right, conditions. Random, it does say that they both come from a simple random sample. Independent, I have to do this for both samples. So my first sample size was 80. These are all students at school 1. These are all students at school 2. Notice it doesn't have anything to do with who did or did not eat breakfast. That's P, not N. N is just who am I taking this sample of. And then LCC. Now notice on this LCC, I do have hats. That's because all the information that I have been given is all sample information. I have no population information. So all of my numbers are from a sample. So that's why I have hats on them. So NP and NQ for sample 1 and NP and NQ for sample 2. Hats on, everybody. Throw your numbers in. And lots of check marks. This is super tedious and really hard to write, and so I've done a couple of these. So what I have found is that it's easier to do NP and NQ and then NP and NQ and then decide if you need hats or not, and then go put your sub numbers. To me, that's the fastest way to write that, because otherwise I get confused. Is it P or Q? Is it sub 1, sub 2? Sometimes I end up putting a sub 1 on my 10. Like, bad things happen. So I have found that the easiest way is just to build it all the way across, kind of in layers. Then I'm going to go to my test statistic. This has not changed. All right, here's what changes. So we're Z because we're proportions. Then I have my statistic difference minus my parameter difference. And then this guy, because this is a test for a 2-sample proportion, I have to kick over here and pool it. And I'm going to label that that's what I'm doing. So I have P hat sub C, and it has a hat on it because this information is coming from a sample. I had 19 kids who went without breakfast in school 1 and 26 without breakfast in school 2. And then those are my 2 sample sizes. Add the top, that gives me 45. Add the bottom, that gives me 230 for a P hat sub C of 0.196. Okay? So make sure that you write the correct standard deviation of your statistic. Don't give me P hat sub 1, Q hat sub 1 over N sub 1. That would be an awful way to lose 2 or 3 points. Okay. And then you would lose points again because you're plugging the wrong information in. So you can write the wrong thing, but plug in the right thing and lose fewer points. Obviously, I'd rather you write the correct thing and plug in the correct thing. So just remember, 2-sample test, pool it. So there's my 0.196. Hold on one second. Yeah. There's my 0.196, and you can see that it's the same in both standard deviations, and the 0.804 is just the knot of that. And then over, but notice that my 2 sample sizes are still different. These are the decimals for each of the individual proportions. I think I wrote that. Yeah, up here, I found it. I just went ahead and wrote that out. And then I went decimal when I went into my formula. Guys, when you're doing your homework, y'all need to type that in. Don't just ride my coattails and write my answer down and assume that you know how to type it in. It really hurts when you have the formula right, but you type it into your calculator wrong. So you need to practice that with your parentheses, because that's a big boy to plug in. Okay. Then I get my z-score, or z. Yeah, my z-score. And then I come over here and find my p-value. I am going to write that I'm two-tailed so I don't forget to double it. There's one of them. There's the other one. So I 2 normal CDF from 1.183 to infinity, and I get a very nice kind of large p-value of 23.7%. So since our p-value is greater than the level of significance for this test, we failed to reject H sub O. There is not enough evidence to conclude that the true proportions of students at the two schools who did not eat breakfast are different. Our data is not statistically significant because it did not make me change my mind. Okay. Guys, that's one from head to toe. That's it. So the really the tricky part here is all the subtractions and the pooled part. And make sure that your conclusion, especially that second sentence, make sure it makes sense. Okay? Most experiments on people use recruited volunteers as subjects. It's kind of difficult to force someone to be in an experiment. When subjects are not randomly selected, researchers cannot generalize the results of an experiment to some larger population of interest. But researchers can draw cause and effect conclusions that apply to the people like the ones who took part in the experiment. We've talked about that before. Also remember, unless the experimental units, so your sample, are randomly selected, you do not need to check the 10% condition when performing an inference about an experiment. So make sure that you're crystal clear. You need to do the 10% condition if a sample was taken. If a random sample was taken, then you have to do the 10% condition. But if I took volunteers, then I don't have a sample. My randomness is in the random assignment of the treatments. So when I get to the 10% condition, I'm going to put not needed because I didn't take a random sample. Okay, so now we're going to do one, and I bet it's going to be an experiment. We'll see. We're going to do one from start to finish. Cholesterol and heart attacks. Usually when medicine's involved, it's an experiment. High levels of cholesterol in the blood are associated with a higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? Sounds like a test. The Helsinki Heart Study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. Okay, pause for just a second. That means, number one, this is not a simple random sample. And number two, I can only project my results onto middle-aged men with high cholesterol but no history of other serious medical problems. That's the only people that I can say if this is statistically significant or not. Then if they do this, then this will happen. If they do this, it causes this to happen in these particular type of people. The volunteer subjects were assigned at random, there's your randomness, to one of two treatments. 2,051 men, that's a great sample size, took the drug gemfibrozil to reduce their cholesterol levels, and then a control group of 2,030 men took a placebo. Now we could have a whole nother conversation about how you should set up that experiment, and should it be blind or double blind, and how long, and how you can control everything, and looking for confounding factors. That's a whole nother unit. Okay, sorry, I got distracted. During the next 5 years, 56 men in the drug group and 84 men in the placebo group had heart attacks. Is this difference statistically significant at the 1% level of significance? Okay, here's my challenge to you. I challenge you to pause me and do this problem. And if you can get all the way through without getting stuck, then great. Then you can play at the end and check your work. If you go a little bit and get stuck, then unpause me until I get to where you are. Get unstuck, pause me back, and keep going. But I would love for you to do as much of this on your own as you can without me, and use me to double check your work. Okay, so pause me. Okay, I'm just going to write out some kind of information to get it out of all the words. So I'm going to put that my first sample size is 2051 and my sample size is 2030. My p-hat sub 1 is 56 over 2051 and my p-hat sub 2 is 84 over 2030. That's not required. You don't get any points for that. It just helps me. Okay, I am a 2-sample z-test for difference of proportions. P sub 1. And this is where, oh my gosh, you want to abbreviate because this is so tedious. But no, you have to practice writing all this out. The true proportion of all middle-aged men with high, I don't know how to spell cholesterol, but no history of medical problems, who take GNMFIBROZIL, and because that's just the sample, had a heart attack. Good gracious. Okay, now because this is the notes, and if you do this in your homework, that's fine. So P sub 2 is going to be all of that stuff, but this is going to say, instead of that, it's going to say take placebo. Or you could say who don't take that drug. I'm totally fine with that on the homework. I'm not okay on quizzes and tests, and definitely not on the AP exam. Now notice, that was painstakingly long, but necessary. All right, so there's all my housekeeping stuff. So I am going to dive into my null and my alternate. And I can use P sub 1 and P sub 2 because I have defined them. Let's see. It says during the next 5 years. Nope. Go back to the top. Will using a drug to lower blood cholesterol reduce heart attacks? Okay, so I want to reduce heart attacks, so that's going to make the drug proportion smaller than the placebo proportion, if it's proportion of people who have heart attacks. So if P sub 1 is going to be smaller, then my difference is going to be negative. There we go. Now you could have also had P sub 1 equals P sub 2 and P sub 1 less than P sub 2. That would have been fine. But make sure you understand why it's less than. Okay, conditions. Random. Yes, because it says random assignment. Now, when I write that right there, because I didn't write random sample because there wasn't a random sample, these were volunteers. When you write that random assignment, that is your reminder that when you get to independent, you can put not needed because not a simple random sample. Don't just put not needed. Tell me why. All right, and now we've got normal, which is the LCC. So here we go. NP, NQ, NP, in Q sample data sub 1, sub 2. Okay. Let's see. First sample size was 2151, 56 over 2051. Yep. And 2051, let's see, the knot of that is 1995. That's good. All right, now let's come over here. So let's see, the second sample size was 2030, and the first proportion was 84 over 2030. And 84 is definitely bigger than 10. And then in Q, the knot of that is 1946. 1946 is greater than or equal to 10. All right, my arm already hurts. Okay, conditions are done. So now I'm ready to go to test statistic, which is statistic minus parameter over standard deviation. Proportion, so this is a z, p hat sub 1 minus p hat sub 2 minus p sub 1, p sub 2 over, all right, this is a test of proportion, so I need to pool it because it's a test. All right, so let me go pool it. P hat sub c. Let's see, successes. 56 and 84 out of, ooh, big numbers, 2051 and 2030, which is 140 over 4081, which is 0343. If you want to do this in your calculator in one swoop, you better make sure you put parentheses around the bottom and parentheses are on the top and parentheses are on the bottom. I recommend going to the 140 and the 4081 and then going decimal. So this is P hat sub C Q hat sub C over first sample plus P hat sub C Q hat sub C over second sample. Okay, so z equals, all right, my first proportion was, now I went ahead and went decimal, 0.0273 minus 0.0414 minus 0 over, which I want you to show, I want you to put that minus 0. And this was 0.0343. And the knot of that is 0.9657. Now notice I went 4 decimal places because the first one starts with a 0. So went ahead and stayed 4 decimal places with my Q. Over my first sample size, which was 2051, and 0.0343, 0.9657 over the second sample size. Okay, now, if you're watching this, you've already done all this. So I hope you have taken the time to type all of this stuff that's in blue on your calculator. You should get a z to be negative 2.475. And if not, you need to go love on some parentheses. Okay, now that I've done that, now I can find my p-value. So let's see, he's negative 2.475, but we are, no, we're not two-tailed. Sorry, we're less than. It was the other one that was two-tailed. So I'm going to normal CDF from negative infinity to negative 2.47501, and I got, I'm not just going to write a number, I'm going to write what it is, p-value of 0.00666 if I go 3 decimal places and I don't like zeros. Now that is a t-tiny p-value. So that is less than the level of significance for this test. Okay, so here we go. I'm not going to write, I'm just going to read it. So yours should already be written. So you should be checking yours. Here we go. Since our p-value is less than the level of significance for this test, and then in parentheses, 0.00666 is less than 0.01, we reject H sub 0. There is enough evidence to conclude that the true proportion of all middle-aged men like the ones in this study, now that's me being a tad bit lazy because I don't want to have to restate have high cholesterol but no history of medical problems. So I can do that by just saying like the ones in this study. Okay, so here we go one more time. There is enough evidence to conclude that the true proportion of all middle-aged men like the ones in this study who have heart attacks is smaller for the group that take gemfibrozol. Taking this drug causes these men to have fewer heart attacks. Our data is statistically significant. So I've got my 3 sentences. That second sentence, be like thorough but to the point. There's enough evidence to conclude that the true proportion of all middle-aged men, like the ones in this study, who have heart attacks is smaller for the group that take the drug. Taking this drug causes, because this is an experiment, these men to have fewer heart attacks. Our data is statistically significant. So hopefully you guys see, because we laid such a strong foundation in chapters 8 and chapters 9, chapter 10 is now just adding like this extra layer with a few things we have to tweak and a couple nooks and crannies, but nothing major. So your foundation is already there. But pay attention to the differences. The most common mistake is people forget to pool their standard deviation, and you pool it when it's a 2 sample proportion test because you are testing the waters in the pool. All right.